walking distance. And if you get here early enough, we even have free parking, which means you don't have to pay for a parking pass. Now let's come inside and view the lab. Both Peter Cummings and Claire McCabe's labs are located here in the Multi-Scale Modeling and Simulation Center, or MUMS. And it's a really great facility that we kind of have all to ourselves just for computational research groups. We have card access to get in. And then in here we have this awesome conference area, which we use as a collaboration space as well as kind of a lunch space. We have fridges, an ice maker, some coffee machine. And then as we walk through here, we kind of have this nice little hangout space. You can read papers over here, chat with a collaborator. And then we have very large desks and lots of large windows. So plenty of natural light coming in since this is our primary workspace. You can see it's really nice to have a nice open space. And both Peter and Claire work right over here. This is Claire's office and Peter's office. And we also have a small conference room in between where we have additional meetings. And now let's jump into some research descriptions.
Hi, my name is Ray Matsumoto. I'm a fifth year grad student advised by Peter Cummings, and I'm on the FIRST Center project. FIRST is specifically a center that is funded by the Department of Energy. We work with researchers at Oak Ridge and other universities where our goal is to understand transport at a molecular level that we can use to develop more efficient supercapacitors. And Shabo, who's also on the project, will tell you a little bit about some of the work that we've been doing.
Yeah, so hi everybody. My name is Xiaobo Lin, and a second year PhD student in Peter Cummings group. So I'm currently working on the MaxIn project. The MaxIn is a two-dimensional material which has recently been found to have great potential to boost the performance of energy storage devices.
All right, hey everyone, I'm Justin. I'm a fifth year graduate student who is co-advised by both Peter Cummings and Claire McCabe. The project I am mostly focused on is the MOSTEP project, or the Molecular Simulation and Design Framework, which is a majority software development where we are developing open source tools for system and molecular system initialization and simulation. One other project we sort of work on as well is one that Ko's going to give more information about in a second, but it's enabling large-scale screening of various molecular systems using MOSTEP. And Ko, I'll let you.
Hi, my name's Ko. I'm also co-advised by both Peter and Claire. So I'm a third year grad student here. So I'm also involved in the MOSTEP project and the same project that both of us working on is the iModels project. So it's a high throughput screening studies where we want to identify the thin film design that we can use to improve the tribological properties of surfaces. So we have worked on this project for about a year, and we have simulated about 40,000 systems, and we're in the process of processing the data now using machine learning.
Hi, I'm Chloe.
And I'm Duncan.
And we're second year graduate students in Claire McCabe's research group. So we do multi-scale modeling of the stratum corneum, which is the outermost layer of the epidermis. In doing this, we employ molecular dynamic simulations, which can range from the atomistic to the coarse-grained scale. In doing this work, we're better able to understand the relationship between structure and the barrier function of healthy and diseased skin at the molecular level.
And what I do is measure the permeability of water through these systems because common skin diseases such as atopic dermatitis and eczema are known to damage the barrier function and lead to a massively increased rate of water loss through the skin. And we have some wonderful collaborators over in the Netherlands who help us to experimentally validate our models.
Hi, my name's Alyssa, and I am a third year in the Claire McCabe lab group. I work on the Statistical Associating Fluid Theory, or SAFT project, which is an equation of state-based approach that we use to describe complex fluids. Specifically, we look at greener solvents known as deep eutectic solvents. And next, we're going to go into some computational resources.
So this is one of the many resources we utilize here in our lab. We have our own supercomputer, which is called Raman, which is exclusively ours, and we also use Vanderbilt's Acre, which is available to anybody at the university, and we also have time on Oak Ridge National Lab and Lawrence Berkeley National Lab supercomputers.
We hope to see you soon!